Hi there, and welcome to the lecture about assembly. Now first, before we start, let me tell you this. We give this lecture because when you start working at a low level, you need to understand assembly. Because if you do not understand assembly, you cannot understand what the CPU is doing. And if we're going to do weird stuff, if we're going to rely on undefined behavior at the level of the C language, what we're really going to do is we're going to see how this undefined behavior is actually still predictable. And to do that, we need to look at the lower level. And to look at this level, assembly is the most convenient language because it tells you a lot about how the CPU works. So, in this lecture and in the remainder of the course, we specifically use 64-bit x86 assembly, right? So the kind of assembly that modern Intel and AMD CPUs use on 64-bit systems. And we do this on Linux and specifically in the AT&T notation. Now, unfortunately for Intel assembly, there are multiple notations and they are pretty different. They can be confusing. So, for example, one thing that the Intel notation does, which is a competing notation against AT&T, it swaps the operands. So the AT&T notation puts the source first and destination second, whereas the Intel notation puts the destination first and then the source. So, moreover, the operand type is indicated differently. At this level, the operating system also matters. So C is nice and portable. It allows us to write code that, except for perhaps the system calls, is identical between operating systems. However, behind the scenes, when it generates assembly, it knows what operating system it is generating it for. So for example, the way a function is called differs between operating systems. They have their own conventions, and if you mix these conventions, the call will not succeed because the function will not know where its parameters are. So, Windows, for example, uses registers differently. Now, if you are already familiar with this particular type of assembly, so 64 x86 on Linux using AT&T notation, then feel free to skip this lecture. So again, I would recommend, if you're familiar with anything else, to at least take a quick look to see if you may be missing something, because the differences can be confusing at times. But if you're already well familiar with this, feel free to skip and move on to the next lecture, because you should learn nothing new here. So first of all, what is assembly? Now, assembly is a low-level symbolic language. It may very well be the lowest possible level symbolic language, in fact. So it is low level in the sense that it's very close to what the CPU is actually doing. In fact, it is so close that it's processor specific. So when you write C code, you will be able to run it on your Intel CPU as well as on the ARM CPU that's in your phone. If you write assembly code, you will only be able to run it on the particular CPU that you write this code for. So you cannot interchange it between Intel CPUs and ARM CPUs, for example. So the language is symbolic in the sense that it allows you to define symbols, that is labels, that it will later determine the address of. So for example, machine code, which is simply binary code rather than the text format, does not allow you to define symbols. Everything that you point to is an address. So there you have to think where to put, say, a function. And then when you refer to the function, you would have to do it with a number that indicates the address of the function. Now obviously, symbolic is much easier because now the address of the function is determined afterwards by the linker and you need not worry about it. You can simply refer to the function by name, whereas in the final machine code, the function will get an address and the labels are automatically replaced by the address. So, assembly code is directly translated in machine code. So every instruction in assembly code corresponds exactly to one instruction in machine code, which means that you're very, very close to the CPU and you can understand exactly what it's doing. So, what does assembly code look like? Well, the core of the assembly code are instructions, which are very simple operations. So basically the CPU is designed to have very simple operations that you combine to together make a functional program. So a typical example would be the move instruction. So the move instruction copies a value from one location to another. In the example, we have two locations which are called registers. We'll go into more detail in what registers are in a bit. And this instruction simply moves the data from the RAX register to the RBX register. Another thing that you might encounter in assembly code are directives. Now these are commands not for the CPU, but for the assembler itself. For example, we might specify which section we are in. If we have an executable file, it consists of sections, and the different sections have different permissions. For example, the data section contains global variables and should be readable and writable, but not executable. Whereas the text segment contains the code. The program code should be executable, but it should not be writable. So these instructions tell the assembler and the linker how to make the final binary, such that it can be loaded by the operating system in a way that the program executes correctly and securely. Some other commands include defining some data. So the byte, word, long, and quad simply output an integer directly, based on size. So byte corresponds to 8 bits, or 1 byte. Word corresponds to 16 bits, that is 2 bytes. Long corresponds to 32 bits, or 4 bytes. And quad corresponds to a quad word, that is 4 times 16, or 64 bits, 8 bytes. Now this is the longest regular integer that you will encounter on a 64-bit system, although instruction set extensions might allow you to work with longer ones. Another form of data is strings. So typically the assembler also helps you in allowing you to define a string, which is simply a series of bytes. And it may or may not, depending on which directive you use, be followed by a null terminator. Now, labels are also very important because, as I mentioned, assembly is a symbolic language. So a label defines a symbol that you can refer to. So if you have a label foo, it means that in the program you can use the word foo to refer to the current address. So this example, .byte42, simply generates in the output a byte with the value 42. Now, because we created the label foo, the assembler is going to remember where this byte was added. Later, if we use the label foo, we're referring to the address where this byte was stored. So this works exactly like a global variable in C. Character foo equals 42. So if we use in C the name foo, we also refer to the memory location defined by the label. Finally, as you may have already seen, there are also comments, namely the text after the hash is ignored. So we can use this to simply put comments for ourselves that the assembler and the CPU will completely ignore. So, as I mentioned, instructions are the most important part of the assembly language syntax, and they do all the useful work. The general form of an instruction is mnemonic space source, comma, destination. Again, here the AT&T syntax that we use differs from the Intel syntax, which swaps the operands. So this means in any Intel manual, you must realize that the operands, compared to what we teach here, are the wrong way around, which can be a bit confusing. So the mnemonic is simply a short code telling the CPU what to do. So for example, mov, which stands for move, as we saw before, is one of the mnemonics, and it refers to an instruction that copies data. Add obviously performs an addition. Sub performs a subtraction. We have push and pop, which manipulate the stack by pushing data onto it or popping data from it. We have the call instruction, which calls a function, and the jump instruction, which jumps to a particular address. So these mnemonics are the different operations that we can get the CPU to do, and they're typically very simple operations. Source and destination are the operands. So they are the data, the pieces of data that the instruction operates on. So these could be different types that we will discuss shortly. Now, the number and type of operands depends on the instruction. So not all instructions take 2 operands, although this is pretty common, at least for arithmetic instructions. So there could definitely be fewer operands, and a few instructions also have more operands. Moreover, operands may be implicit. So for example, the push and the pop instructions manipulate the stack pointer, as well as the data that is stored at the location that the stack pointer points to. This is not explicit in the instruction. So these are implicit operands to the push and pop instructions. And some more instructions have implicit operands. Now, these are the different types of operands that you can get. Registers, memory, and constants. So registers are typically the simplest ones. A register is a simple, small memory location stored on the CPU itself. So access is super fast, but the amount of storage is limited. We only have a few registers and they're very small. If we need to access more data, we can use a memory operand, which is essentially what we know in C as a pointer. So a memory operand specifies the address where we're going to access data and then references that data stored in memory. So examples, and this is a bit confusing perhaps about the AT&T syntax. If we write a number, including for example the 0x401000 that we should see here, by default it is a pointer. By default it refers to memory. It refers to the memory location specified by the number. So it doesn't refer to the number itself, which would be a constant. Okay? So other cases we can also construct pointers, computing them. So for example, the second example is RBP register plus 8. It computes this number and then uses it as a pointer, dereferencing the pointer to get the memory address that it points to. The other one, for example, also computes something. It computes RDX plus RCX times 4. Well, why you do this or how you can in general provide these memory operands, we will discuss later. So one restriction is that only one explicit memory operand is allowed. So for example, you cannot use the mov instruction to copy from one memory location to another. However, if the memory operand is implicit, this is possible. So for example, you can have a push instruction that pushes some data from memory onto the stack, which is also in memory. Finally, we have constants, also known as immediates in the context of assembly language. So immediates or constants are marked by the $sign. So if the $sign is not there, you're referring to memory instead. So $32 refers to the number 42 itself, rather than the data stored at address 42. Likewise for $sign 0x401000. These refer to the number itself. So if for whatever reason we want to store the pointer somewhere rather than the data that we point to, we also need to use the $sign to indicate that we want to make an immediate rather than a memory access. Now, I already mentioned registers. So registers are basically the operand types you want to use most of the time. A register is a small memory location on the CPU itself, and access to the registers is super fast. It takes no extra time to access a register, whereas a memory access takes considerable time compared to the time it takes for the CPU to compute a value. Right? So for performance, we want to use registers whenever we can. Now there's a large number of registers available, but only some are used most of the time. So the most used are the general purpose registers, which are RAX, RBX, RCX, RDX, RSI, RDI, and a number of numbered registers, R8 up to R15. So in 64-bit assembly, there are 16 normal named registers, but 2 of them are not considered general purpose. So RSP is the stack pointer, which points to the top of the stack, and it's not considered general purpose. So it's used implicitly in quite a few instructions, and as such, it cannot be used for general usage. The frame pointer, RBP, is also considered to be not a general purpose register. It points to the current stack frame, and it also has some special encodings, unlike the other registers. However, it can and often will be used for other purposes. So if we tell the compiler to optimize it may choose not to create stack frames with an explicit frame pointer, using the stack pointer instead. In this case, RBP becomes freely available as a general purpose register. So this makes the system faster, because the registers are the fastest memory locations we have. So if we can use more registers, we can create faster code in the compiler. Well, there's also the flags register, which is very important, but we cannot access it directly. So the flags register stores the state of the last computation. For example, it might remember whether the computation resulted in a 0 or in a negative number. Now we can push the flags onto the stack and pop them again from the stack, but there's no instruction to directly write to the flags register itself. So there's also a number of other special registers. For example, RIP is very important. This is the instruction pointer. It points to the instruction that the CPU is currently executing. Now again, direct access to the instruction pointer is limited. We cannot read the memory pointer, although what we could do is perform a call and then read it from the stack. However, we can write to it using an instruction like jump. So jump essentially just sets the instruction pointer to another value, ensuring that execution continues there. We can also use the instruction pointer in memory references, which is very useful because it means that when our code moves around and the data moves with it, our references are still correct. So in this case, we are no longer bound to use a fixed memory address to store our program, but we can use RIP relative addressing, and we can move the program around without any issue with the memory addresses changing. Now, there's also a bunch of segment registers, namely the code segment, the data segment, the extra segment, stack segment, and two extra segments called FS and GS that don't really stand for anything. But these are rarely used in 64-bit systems. So these are mostly legacy, although FS and GS can still be used to some extent. There's also a whole bunch of system registers, so the control registers, the debug registers, and the model-specific registers. However, you're only allowed to use these in the kernel. So these registers are generally not directly accessible outside the kernel. And then there's a whole bunch of registers. This is probably more than all the others put together, well, except for the MSRs maybe, but these are instruction set extensions. So whenever the CPU is extended with more instruction sets to increase performance, it's fairly typical to also add registers that are specific to this instruction set extension. So the oldest one is the FPU, the floating point unit, and it has the %st registers, which are the floating point stack. Later instruction set extensions include MMX and SSE, which has several versions, and these also define their own registers. Now, unlike what we've seen before, these registers may actually be larger than 64 bits. So for example, an FPU register storing a floating point number is actually 80 bits, and later extensions even have 128 or larger registers. So these registers can only be used with special instructions, and they're generally used for special purpose computations, including floating point, but also vector computations, and stuff that's basically used for video rendering and other media processing related stuff. Right, so these instruction set extensions for this course are not of particular importance, but for a performance-oriented course might be relevant. So, the default registers, the general purpose registers that I discussed, are 64-bit, because we have a 64-bit machine. But of course, Intel would not be Intel if there weren't a lot of legacy. And for these legacy reasons, and also because they are often convenient, we also have smaller registers. And these smaller registers are actually part of the larger registers, which means that if you change the smaller register, the larger one also changes, and vice versa. So, again, for weird legacy reasons, this behavior is also inconsistent. So, if you have a 32-bit subregister, then if you set it, the other bits in the 64-bit register will be cleared. That is, all the higher order 32 bits will be set to 0. However, if you take the smaller subregisters, which are 16 bits or 8 bits, then you retain the other bits, including even those upper 32 bits. So this behavior is a bit inconsistent, but it can be convenient because it means that sometimes you can use the 32-bit register to set the full 64-bit register, which can be useful because it's not possible for most instructions to have 64-bit constants, only 32-bit ones. Right, so essentially the behavior means that you can use the tiny registers, 8 bits and 16 bits, to combine data into a 64-bit value, and the 32-bit registers you can use to set a constant that has the uppermost bits all set to 0. Obviously, this does not, however, work for negative numbers, given how we discuss that the system is two complement. This will be discussed later. Now, if you look at the diagram, you see how this works. So we show the large register, which has 16 hexadecimal digits, right? So every hexadecimal digit corresponds to 4 binary bits. So that's a total of 64 bits. Then the RAX register, which is a default general purpose register, contains all this data. Well, the EAX register contains the lowermost 32 bits, low order 32 bits of this large register. Then we also have AX, which contains the low order 16 bits. And finally, we have AL and AH, which contain the lowest order byte in AL and the second byte in AH. Again, this all exists for legacy reasons. Right? Even the names exist for legacy reasons. Obviously, AL and AH were originally the lower and upper byte of the AX register. Then we extended the AX register to call it EAX. And finally, we extended it again to call it RAX. This is how the current situation came to be. Now this table shows all the general purpose registers, including the stack pointer and the frame pointer, which are not entirely general purpose, but which are still treated in this way. So, at the top you see the default registers, which contain all the 64 bits, and they all start with the R. Now, the lower 32 bits basically replace the R with an E. However, the numbered registers at the end still have the R, but then have a suffix specifying the size. Again, lots of legacy. These registers are new. They didn't used to exist in the original 32-bit architecture, so they had to come up with new names here. And this is apparently the best they could do. The lower 16 bits basically removes the R or the E, right? Except again for the numbered registers where there's the W. So the D stands for double word and the W for word. Because originally the 16-bit system, the 8086, the 16-bit system, had a machine word that was 16 bits. And basically, when the machine word got larger, they didn't dare to rename this. So we still use the word word to refer to 16 bits. And then we have the bytes. So only the old registers, the RAX, RBX, and RCX, and RDX have the second byte, again for legacy, but all of them have the lowest order byte. Right, so this is indicated by the L. Okay, well, these are all the registers. Not all of them are necessarily useful. I've never encountered a use case, for example, for getting the lowermost byte of the stack pointer, but the benefit is that they do allow you to natively work on smaller integers, such as the char or the short in C code. Right, the benefit here, of course, is that you don't need to do multiple reads and writes when getting these things from memory and composing them. You can just get only an individual byte or write an individual byte, which can be useful for some programs. So, now that we have discussed registers, let's get to the other very important type of operands, namely memory operands. So unlike C, memory is always accessed by explicitly dereferencing pointers. So in C, we might declare a variable, and we won't even know whether it lives in a register or in memory. But in assembly code, we must always make a choice, and we must always be explicit. So any memory reference dereferences an explicit pointer. Well, Intel is an assembly language that's pretty much as close as you can get to a high-level language, in the sense that it allows us to do all sorts of elaborate inline pointer computations, which means that in the general case, a pointer dereference looks like this. displacement, open parenthesis, base, index, scale. So all of these parts are optional. And in the end, they compute an address that will be dereferenced. So the address is computed essentially at the same time the instruction is executed. So this is very fast. But it introduces a lot of complicated syntax and circuitry in the CPU. So this computes the following address: displacement plus base plus index times scale. Okay, so essentially the idea is here that we can have an array reference without extra specification needed, right? So without first having to separately compute this, everything can be specified in only one indication, only one dereference of the memory. So the operation computes and dereferences the pointer. Well, here the base and the index are always 64-bit registers. The displacement is a 32-bit constant or a symbol. So we are able to reference a symbol that was defined by a label, and otherwise we can just put a number there. The default is the displacement is missing is 0. So then you just get what is between the parentheses. The scale can be 1, 2, 4, or 8. And this is used to multiply the index by. So essentially it's implemented as a shift, as you can see from the numbers. So the default is to have 1 here, which means that you get the index literally. Now, all these parts are optional, and there's another variation that is possible. So the base register can be RIP. So normally only the general purpose registers and the stack pointer and base pointer are allowed, but RIP is also allowed as a base. And in this case, the symbolic displacement, so if you put a symbol as a displacement, it is made relative. So then rather than being translated in machine code in an absolute address, saying variable foo is at address 0x, say 400,000, instead what you get is this location is at RIP, so the current instruction pointer, plus or minus a much smaller number. And this means that if you move the code around, that the reference stays the same. So you can move the code without having to recompile it, which is often very useful. So on this slide there's a number of example memory operands. So for each of them we will show the C code that this would correspond with, to give you some idea of why you would use these particular constructs in assembly code. So the first one, REX between parentheses, the computation is very simple. There's just a base, which is REX, and everything else is 0. So we just use REX, the value stored in there, as a pointer and dereference it. So then we get whatever data was stored at the memory location REX. So what does this correspond with in C? It corresponds with a simple pointer dereference. So we declare the P, which here we define as a long pointer simply by default. The memory operand doesn't indicate what the size actually is, so we just take a long as a default, but it could have also been an int or a short or a char. That would have also been possible depending on the context. Right, so this is simply a pointer dereference, and the value of the pointer obviously is REX. Well, if we have just a number, it's also interpreted as a memory operand. So in this case, the parentheses are missing because this is only the displacement. So what does this correspond to? Well, we have this particular memory address and we dereference it. So typically this memory address would actually be the location of a variable, right? But we cannot see the name of the variable in the assembly example. Now the next one, -8 RBP. So we take the base pointer and subtract 8 bytes, and then we dereference this. Now this, we will see later, is exactly how you normally reference a local variable. So in this case there must have been some local variable, let's call it foo for now, and that local variable is being accessed. As you can see, in C we no longer have an explicit pointer dereference. C just allocates this variable on the stack and knows that it is at -8 RBP, because that is the location on the stack it reserved for it. But the programmer doesn't know this is a pointer. It might actually just as well be allocated as a register. So now the next one, simply foo, this is a global variable. So a global variable does have a label in the assembly code, and this label indicates the address. So when you link the program, it finds out what the final address is and puts it in. Right? So the foo is replaced by the address. Well, in C these two look the same, but here you can see that the compiler decides where to allocate the memory depending on whether this was a local or a global variable. So now the next one, foo plus rex. Well, this is a typical example of an array index. So we have an array foo. We have no idea how large it is. This information is not encoded anywhere in the assembly code. The size information just gets lost unless you explicitly keep track of it. So we have a character array foo and an index which is a long, because in this case rex is the index. Right, so we dereference foo by indexing it with the index. So this simply, because the elements are size 1, simply takes a pointer to foo and adds the index to it, which is exactly what the assembly code also does. Now the next one. We omitted the base here and instead added an index and a multiplier, a scale. Right, so what does this mean? Well, it's the same except for the array type. So in this case we multiply the index by 8. And this is typically seen for array indexes, where you would have an element size of 8. The next one, foo, and then between parentheses RIP, which is the instruction pointer. Now this is also simply a global variable foo. However, now we told the compiler to generate position-independent code, which means that if we move the code around, that the earlier reference, just foo, no longer works. It references the same address, but that address is no longer in the right location. Okay, because the code moved. So, now the next one. RAX plus RBX times 4. What does this mean? So, RAX is the base and RBX is the index, which is multiplied by 4. Now this is typically a pointer that's indexed as an array. So we have a pointer p and it points to an int, because we know the element size of the array is 4, because that is what the index is multiplied by. So an int is by default on the architecture that we consider is by default 4 bytes. Okay, so we index it with an index which is again a long. Now finally we have one that has all the parts specified. A displacement of 4, a base of RAX, an index of RBX, and a scale of 8. Well, what is this? This is again an array reference, but now there's also a struct involved. So the struct that we specify here has two members, A and B. So the total of the struct is 8 bytes, which is why there's a multiplier of 8 in the memory specification. So 4 bytes for A plus 4 bytes for B. And then within the struct, we have another offset of 4, which indicates that we're referencing member B, which happens to be at offset 4. So these are typical ways in which the memory operands correspond to what you would see in C. So as I mentioned on the previous slide, if you just have the memory operand, it doesn't actually specify the size of the memory reference. And in fact, some of the cases that we identified by the element size through the scale might actually have been structs containing smaller members, of which means that we only access part of the array element. So instead we need some way to specify how large a memory reference actually is. Well, in AT&T syntax we do this using a suffix to the mnemonic. So if we add a B to the mnemonic at the end, it means that any memory reference in there will reference a single byte. The W means it references a word, or 16 bits. The L means it references a long, or 32 bits. And finally, Q stands for quad word, so that is 64 bits, the entire machine word. So this is interesting, by the way. if you look at these letters closely and look at the ones used for the registers that are numbered, you will also see yet another nice inconsistency. So when working with Intel, always keep in mind everything is inconsistent and you just have to get used to it. So another important thing, these suffixes are only required if it's not possible to determine what the size of the memory operand is from the context. In particular, if there's also a register operand, it's optional. Each register clearly indicates what its size is. So the name implies the size, which means in this case the memory operand is taken to be the same size as the register operand, and a suffix is not needed. So to give a simple example, MOVW means move with word size. $1 is an immediate value, so just a constant 1. And then we have a memory operand, which is a pointer to REX. So we're storing the 1 at the memory location REX. So in this case, because there's a W there, we store 2 bytes, which means the 1 byte, which is a low order byte, as well as a 0 byte following it. So on the last slide, I was already kind of implying this, but let's discuss this explicitly. If we store an integer in memory that consists of multiple bytes, it's not obvious in what order we store the bytes. There's 2 possible ways. Now, in fact, there are more possible ways, but the other ways don't really make a lot of sense. There's 2 ways that make some sense. The least significant byte first, or the most significant byte first. Now, we refer to these as the little end or the big end. So, if we store the least significant byte first, then the system is called little endian, because it starts with the little end. If we start with the most significant byte, then your architecture is called big endian. So the Intel architecture is little endian. So, and as in the example I mentioned on the last slide, it starts with the least significant byte. So, to give some example, if we perform a 32-bit store of the value hexadecimal 10,203 at the memory address hexadecimal 1000, it will store the 03, which is the lowest order byte, the least significant byte, at the lowest memory address, which is 1000. Then the next byte, 02, is stored at 1001. The next byte is stored at 1002. And finally, even though it's 0, and you cannot see it in the default notation, there's also a 0 byte. That is the most significant byte, because we have a 32-bit store. And this one is stored at 1003. So, looking on the picture, you might recognize if you've read the book, but this endianness business, this terminology, is actually derived from Swift's book Gulliver's Travels. So this was about a man who traveled to a number of islands. And these particular islands, there was a war between 2 peoples. And these peoples fought over a religious question. Which end of the egg should you open? And there was a number of religious wars on this. So basically what they wanted to show, this was actually an analogy for the religious wars in Europe at the time. But basically the point here, when people named it little endian and big endian, was that this is basically a silly difference. But it still matters enough that wars are fought over it and people can have strong preferences. So in principle, even though little endian is better, it doesn't really matter in the end. x86 allows you to use both signed and unsigned integers, where a signed integer is obviously one that can be negative and an unsigned one cannot be negative. So what you get in return is that the unsigned integers have a larger range at the top. Intel uses 2 complement notation to store signed integers. And this means that the most significant bit is made negative. So as you may know, in binary notation, each bit corresponds to a power of 2. So bit 0 has a value of 2 to the power 0 or 1. Bit 1, that is the second least significant bit, has a value of 2 to the power 1 or 2, and so on. Now, in case of 2 complement notation, the most significant of these bits, the bit with the highest number that is available, has its sign flipped. It's made negative. So, to give an example, in 8 bits, we have this number in binary 10001001. Now, let's see how we compute this. So first we see which bits are in there. Well, that's bit 0, so the least significant bit, bit 3, and also bit 7, which is the most significant bit. Well, now let's compute the value. So 2 to the power 0, which is 1, plus 2 to the power 3, which is 8, minus 2 to the power 7. So minus is because this is 2's complement, and we subtract the highest order bit, which means that if the most significant bit is set, the number is always negative, because the most significant bit has more value than all the others put together. So we subtract 128 and we end up with the value, feel free to compute it for yourself, of minus 119. So let's give a number of examples. So these are all 64-bit numbers shown in hexadecimal. Now if we want to make the smallest number possible, we only set the most significant bit, which is the first example, which is 2 to the power 63. Right, so only bit 63 is set. Now, if we want to make minus 1, we have to set all the bits. Why is this? Well, the negative highest order bit is exactly one more in magnitude than all the other bits put together. So we have minus 2 to the power 63. The remainder of the bits is exactly that, but minus 1. We subtract and we get minus 1. What this also shows is if the number gets smaller, that is more negative, you also see that this works as a regular subtraction. So minus 2 is the same thing, but ending in an E. So we subtracted 1 from the F and we get a number that's lower by 1. Right? So this is a big benefit of 2's complement notation. The arithmetic works essentially the same. So the final example is the highest number that you can get. So, how to do arithmetic on signed integers? Well, fortunately, as I mentioned, it's fairly easy on 2's complement notation. The first one may be a bit counterintuitive, but the math works if you think about it. To flip the sign, so to make, say, 10 minus 10, or to make minus 10 10, you flip all the bits, so that's a bitwise not operation, and then add 1. Again, just do the math and you'll see that it works out. So that, for a CPU, is a very simple operation to do. Most operations are actually identical between signed and unsigned. So addition, subtraction, and so on, they'll all work the same regardless of whether the number is signed or unsigned. And in the end, it's just how you use the number that defines the interpretation. However, comparisons do require a different condition code. So the math is the same, but you need to check a different condition code. Well, another one is multiplication and division. So these require different instructions as well to indicate whether the numbers are signed or unsigned. However, most operations are the same. Well, now there's another issue. What if we have a small integer, so that is, say, an int, and we want to make it into a larger integer, let's say a long? Well, now we also have to consider the sign. If we simply extend the size and replace whatever is in the uppermost bits with the 0, right? Then we will never get a negative number, because the highest order bit will still be 0. So that doesn't work. Instead, what happens is you do sign extension if you're going to upcast a signed integer. Sign extension means you take the most significant bit and you copy it into all the other bits. And it turns out, again, you can do the math if you want, that this works to get you exactly the same number, but with more bits. Alright, so as the example shows, the first one, that is 12, or hexadecimal 0c, would be cast to a larger integer by simply adding zeros as before. Now the zeros are meaningless and they result in the same number. So again, hexadecimal c. If we have a 1 byte, so 8 bits number, 8c in hexadecimal, that is the second number, then what happens if we're going to upcast it to a word, to a 2-byte integer, we need to extend the sign. So you see the highest order bit in the byte is simply copied into all the higher bits that are in there, right? Rather than adding zeros. So in this case, the resulting number will be negative. And it turns out this is still exactly the same number, except now using more space to store it. So now that we've had quite a bit about Intel assembly, let me give you some examples. Please try to work out for yourself if you can understand what these examples do. I would recommend that you pause the recording right now before I give the answers. So now I'll be giving the answers. So the first one, it has a source operand REX, which is on the left, and the destination operand REX, which is on the right. The mnemonic XOR performs an XOR of each bit with each bit from the other operand. So it means every bit of REX is XORed with another bit of REX, with say the same bit of REX, right? Well, what does this do to REX in the end? REX becomes 0 because something XOR itself is always 0. Next one, movq $42 and then a hexadecimal address. So what happens here, the hexadecimal is indeed used as a pointer, and we dereference the pointer, it's the destination, so we store a value there. On the left hand we have an immediate or constant value of 42, so we store the value 42 at the given memory location. Now this is a movq, so there is a q prefix, which means the operation is 64-bit. So we store a 64-bit number with the value 42 at this address. Next one. Hey, that's weird, right? Why do we use such a weird displacement here? Well, remember that the displacement is 32-bit. And then think back about my slide about two complement notation. So this number is actually 8. So to give you an easy way to figure out why this is 8, remember that addition and subtraction work the same way with 2's complement notation as they do with regular unsigned numbers. So what do we need to add to get 0? Well, that's simple. We add 8. So we add 8, we carry over 1 to the next digit, right? So the f becomes again a 10, hexadecimal 10 or 16, and which carries over to the next, and so on and so on. Finally, the carryover is lost at the end, at the highest of the 32 bits. So we end up with 0 if we add 8. That is, this number is actually minus 8. So we take RBP minus 8, which is an address. We dereference this pointer and store the result in the AL register. We have no suffix, but AL implies that this is 8 bits or 1 byte. The next one is a comparison. So we compare two numbers with each other. On the left hand we have a constant 0. On the right hand we have a memory operand that is symbolic. It has shellcode, which is a label, and then it adds REX before dereferencing it, which means that we're referring to the RAX byte from shellcode onwards. Well, then we're comparing this as a byte because of the suffix to 0. So we're simply checking whether the byte number REX is actually 0. Well, we can have a conditional jump later on checking the outcome of this, but we'll still discuss this later. So next one, subtract source operand REX, destination operand is another memory computation. The base is RDX, the index is RCX, and the scale is 8. That is, we have an array with elements of size 8 that starts at the address RDX, and then we take element RCX. Okay? Now, as for the subtraction, the source value is subtracted from the destination value, and it is stored again in the destination. This means we take the array element, subtract REX from it, and then store the result back in the same spot. Okay? Well, I hope you understood. Of course, if you don't, feel free to ask in the Q&A session or on the discussion board or otherwise. Now let me quickly go through a number of mnemonics that you can use to do common instructions. So far I've mostly assumed that you just understand what the mnemonic means, because in most cases it's actually fairly obvious. But let's go through these so that you have some idea of what is out there. First one, move source, destination. Simply copies the value source and stores it in the destination. So it's essentially an assignment. Exchange is different in the sense that it has two destinations and it swaps them. Push pushes a value source on the stack, whereas pop removes a value from the stack and stores it in the destination. Now, arithmetic instructions. So there's a bunch of computations that we can do on the CPU, and I will only discuss the ones that you're most likely to use. So feel free, of course, to check the manual for more. Addition is simply add. We take the destination operand, we add source to it, and store it back again at the destination address. Likewise, subtraction does a similar thing. Then we have increment and decrement instructions, which add 1 or subtract 1. We have a negation instruction, which replaces the destination with its negative value, right? So this is what we discussed in two complement notation. It flips the bits and then add 1. And then finally, what the comparison does is it sets the flags. We'll discuss the flags later when we consider how conditional branches works, based on source 2 minus source 1. So compare is essentially just a subtraction, except it doesn't store the result. Instead, it sets some flags based on the result, which allows you to do a conditional branch based on that. Now, the bitwise operators are again fairly obvious. The AND operation performs an AND on every bit and stores the result in destination. The OR operator, the XOR operator, and the NOT operator all do essentially the same thing. And then finally we have test. So this one is equivalent to compare, but rather than a subtraction, it performs an AND operation. Right? So it allows you to, for example, mask some flags and then check what the result is. So now we get to branches. So I use the term branch to refer to a branch in the control flow graph. Right? So a place where the control flow graph basically splits off. So these unconditional branches will always go to the same place, whereas we'll later discuss some conditional branches that may or may not perform a jump. Essentially, a branch can also be considered a write to the instruction pointer RIP. So the first jump simply jumps to the specified address, or in other words, it sets the instruction pointer to the address. Call will push the return address, that is, the address of the next instruction after the call, and then go to the function. So it retains the old RIP and then changes the RIP. Ret performs a return and it's executed at the end of a function. So it pops the return address back from the stack and returns to that address to get back to the place right after the earlier call instruction was executed. And finally, syscall is a different kind of call. It goes into the operating system kernel and has the operating system kernel handle whatever request we tell it to handle. The request is stored in the registers, and we will discuss how this works later on. Then there are some other instructions. LEA means load effective address, and what it does is it computes a pointer and stores the pointer in memory. So the source must be a memory operand and it will not be dereferenced. Instead, the system computes displacement plus base plus index times scale and stores this in the destination. Finally, there's also a NOP or no operation instruction, which does nothing. Now, why would you want this? We will find one application for sure in the lecture on attacks. Now, conditional branches. So conditional branches are conditional in the sense that they may or may not perform a jump, depending on the situation. Why would you want this? Well, this is what you use to implement the if statement or to implement a while loop or something like that. There, you need to perform a test and then either perform a jump or go to the next instruction, depending on the outcome of the test. So, conditional branches have the general form of the letter J followed by a condition code, which we refer to as CC here. So the CC is replaced by an actual condition code. And then you specify the address. Now this instruction only jumps to the address if the condition CC holds. And if this condition CC does not hold, it does nothing. So it just continues to the next instruction. Now all the conditions are decided by the flags register. So I mentioned this flags register before. It is implicitly set by many arithmetic and bitwise instructions based on the result. So for example, if the result is 0, it will set the 0 flag in the flags register. If the result is not 0, it will clear this flag. If the result doesn't fit in the register, it will set the carry flag. If the result doesn't fit in a signed integer, it will set the overflow flag, and so on. So there's a number of flags that tell us something about the result of the computation. These are the common condition codes, and there are a few others that you will rarely use as well. So what do we have? We have, for example, the E and the Z, which have the same meaning and encode the same instruction. And they mean the result is 0. So if we have JZ, it means jump if 0. If the last computation resulted in the number 0, it means it jumps. If it resulted in some other number, it does not jump and continues executing the next instruction. Now why is this the same as equal? Well, that is because of the way we describe the comparison operator. So the compare operator was simply a subtraction. If the two arguments that we give are equal, it means that the value after subtraction becomes 0. If we subtract something from itself, we get 0. Right? So this is why 0 and equal are the same condition code, exactly. Well, then we have comparisons below and above, which refers to what you would expect. The one is larger than the other. So above and below refer to unsigned integers. If we perform the comparison on a signed integer, we need to use another one, because then it uses a different condition flag. In this case, we use less and greater. Now, then we also have the sign bit, which sets a flag. So if the result is negative, then it sets the sign flags in the flags register. Finally, we have NCC, where CC is again replaced by a condition code, and it means not. So we can test for a condition, we can also test for the opposite condition. So JNZ, for example, will jump if the last result was not 0, and it will continue if the last result was 0. So, some examples to give you some idea how this works. So the first example, does compare RBX, RAX, and then jump below. What does this mean? It takes RAX and subtracts RBX from it. Now it doesn't store the result, it only sets the flags register. So if we jump below, it means that we perform an unsigned comparison. And in this case, because of below, we check whether RAX is smaller than RBX. Remember that we were subtracting RBX from RAX, which is why the order is like this. Next one, jump not less. Jumps if RAX is greater than or equal to RBX. And these are the signed ones. Now another one, so here we see the purpose of the test instruction. If we test RAX against itself, the result of the AND operation will be RAX itself. So the result will be 0 if RAX is 0 and non-zero if RAX is also non-zero. Finally, here we have another comparison. So we compare RAX against 0. That is, we take RAX and we subtract 0 from it. So in case now that RAX is negative, then we will see this in the flags. If it's not negative, then the sign bit will not be set. So we can use JNS to jump based on whether RAX is negative or not. So the C compiler uses assembly instructions to implement the language features of C. And conditional branches specifically are used to implement control structures such as if and loops. Okay, so let's take a look how the compiler uses them to implement an if statement. So on the left, we see the rateStudent function, which mainly consists of an if statement. So it takes the value stored in the parameter, compares it to 10. If the value is larger than 10, it executes the if, otherwise it executes the else. And in the end, it returns the value. So then let's take a look on the right-hand side. We have the function rateStudent. It starts off with some junk that we will consider later. But the takeaway from that junk is that it stores the parameter in RBP minus 20. So then the next instruction is the actual comparison. We have a compare instruction with a constant 10 and the location where the level was stored. So we compare, that is, we subtract 10 from the level, and then we have a conditional jump. The condition here is JLE, which means less or equal. We have a signed comparison, which is because the level variable was an int rather than an unsigned int, right? So we have a signed comparison, and we're going to jump if the value is less or equal. Now note that this is the exact opposite condition from the one we find in the C program. Why is this? We're jumping over the if clause. So the assembly code is essentially here in the same order that we have the C code. First we get the if clause and then the else clause. Now what we see? We conditionally jump over the if clause in case the condition does not hold. In case the condition does hold, we continue executing. And then we load the value and store it in the value verdict. Then again we see a jump, but this time it's unconditional. So this jump jumps over the else part of the if statement, so that we execute only the if part. Then at L2, label 2, we see that there's the code that is executed for the else part. There at the end, the code paths merge again. So the if part jumps to L3, whereas the L2 part that implements the else part of the if statement simply falls through into there. It doesn't need to do another jump. So in both cases, we perform one jump. In the if case, we jump over the else. In the else case, we jump over the if. And then at the end, the function simply returns. So now we've talked about the most important instructions and how to use them. However, it's also very important to understand the memory organization if you want to write programs in assembly code, or even just understand them. So for the memory organization, the stack is critical, because the stack stores the local state for functions. So let's try and see how the stack actually works. So the top of the stack is identified by the stack pointer. The stack pointer points to the last operand that we pushed onto the stack. Or of course, if we popped it in the meantime, to one that we pushed earlier. Right? So entries on the stack are always 64-bit. We have no choice here. We can of course use only a part of the 64-bit, but if we increase or decrease the stack pointer, it must always be with a multiple of 8. And we're not supposed to allow the stack pointer to become unaligned. So the stack pointer is always a multiple of 8 for this reason. Well, the push and pop instructions stores a new value on the stack and remove it from the stack. And they implicitly store to the RSP location or load from it. So the stack grows downwards, which means that the more you push, the lower the address becomes where you're pushing. So it starts off with a high address, and as you go, the address becomes lower. This, it turns out, is very important for exploitation, which we will discuss later. So every push decrements the stack pointer by 8, whereas every pop increases it by 8, removing the last value that was pushed. And not popped, of course. And finally, the call and read instructions also use the stack implicitly. So call stores the current address, or actually the next address, so the address of the next instruction, to the stack, and the read instruction pops the address from the stack and jumps back there to basically get back to wherever the current function was called before. As I mentioned, the stack is critical for storing the state of functions. So this is where the term stack frames becomes important. So every function, when executing, gets a stack frame. And the stack frame stores all the local state for this particular function. Now typically, or traditionally perhaps, RBP stores the frame pointer. That is, a pointer to the current stack frame. Now this is not strictly required. So the CPU optimizes for this case in its encodings, but does not enforce this. So you could use RBP for other purposes, and this is actually commonly done after compiler optimizations. However, for now we will just focus on unoptimized code, and this always uses RBP to find the stack frame. This is also useful, for example, when debugging. So when you get a stack trace, it's actually using RBP and all the old values of RBP to find where the different stack frames are for each of the functions currently executing. So every function contains a prologue that sets up the stack frame, at least when not optimized. Every unoptimized function also contains an epilogue, which restores the caller stack frame. Right? So the function itself is responsible for making sure when it returns to the caller that the stack is in such a state as the caller expects. It basically has to clean up its own mess. Finally, in x86-64, parameters are preferentially passed in registers, so they are not stored on the stack. However, it can still happen if for whatever reason the parameters do not fit in the registers. Then the stack may also be used for parameter passing. So in the 32-bit case, this was actually the default. So I already mentioned parameter passing, so here we have some more detail. Before we call a function, the caller is the one who prepares the parameters, because of course the caller knows what they want to pass to the function. So integers, pointers, and small structs, where small means 64 bits or less, are stored in the registers. And we use the registers from left to right: RDI, RSI, RDX, RCX, R8, and R9. So the first parameter uses RDI, the second parameter uses RSI, and so on. Other parameters that do not fit in the registers, either because they are too large or because there's too many of them, are pushed on the stack. And this seems a bit counterintuitive, but they are pushed onto the stack from right to left. Now, some reasoning behind this might be, if you do it like this, it ends up in a logical sequence because the stack grows downward. Because the first one you push ends up at the highest address. Right? So the parameters in memory are basically stored from left to right. Note, all of this is specific to Linux. Other operating systems can use different conventions, which means different registers, or they might use the stack more, they might use the stack less, they might do a different order, and they might have different conventions, for example, on cleanup. This is just what Linux does on 64-bit. So, to give an example, if you have a function with 9 parameters, well, first of all, you should think again whether it's really a good idea to make a function with 9 parameters. And second of all, when you compile it, it will look a little bit like this. So it's going to move all the parameters into the registers from left to right. So the first 6 parameters are stored in registers. And then from right to left, the remaining ones, so starting with 9 and ending with 7, are pushed onto the stack. And then we call the function. And because we strictly follow these conventions, the function knows exactly where to expect its parameters. So, I mentioned the function prologue. The function prologue is used to set up the stack frame for the current function. First thing it does is make sure that it's later able to restore the old state that the caller was expecting. So, it's going to push the old base pointer, that is the RBP register, onto the stack to be able to later restore it in the function epilogue. Next, it sets the base pointer to the current stack pointer. And this is effectively where it's setting up its own stack frame. So it's remembering the stack pointer so that if it pushes any data, the reference to the variables remains the same. Right? The reference to any of the variables in the stack frame can be made using the base pointer now. Well, next, it will push all the registers that must be preserved for the caller. So the operating system, in this case Linux, defines which of the registers are allowed to be changed by functions. So they're essentially scratch registers. Whereas the other registers must be retained when you make a call. This means if the function needs to use these registers, it must push them in the prolog and restore them from the stack in the APlog. So in Linux, this is RBX and R12, R13, R14, R15. But an operating system can make any definition it wants, as long as it's consistent between all the programs, all the libraries, all the compilers. Because this must be the same for the code to be able to interact by means of function calls. Well, next, there's some code that moves the stack pointer to make room for local variables. So, because the stack grows downwards, it's going to subtract from the stack pointer. Well, with these steps, in a simple case where there's no registers to be preserved, you get the snippet that is shown below. Push RBP, move RSP to RBP, and then finally subtract from RSP. At that point, we've allocated space for the local variables. So subtracting from RBP is effectively the same as pushing several times, except that we do not initialize the data that's stored there. This again will be relevant when we're talking about security. And the reason to do it like this rather than with push is to save some time, because now we don't need to write to the memory that we just allocated. Well, moreover, another optional thing that it can do is preserve the parameters into local variables if needed. So this is right after the prolog, but it's still something that you see often in the assembly code. This is because RDI, RSI, RDX, and the other registers used to pass parameters are also scratch registers, and the compiler wants to use them to generate efficient code. If you do this, you must store them onto the stack, because otherwise they will be overwritten. Now the function APlog. So we had the prolog, then the function did some useful work, presumably, and in the end we get to the function APlog. Now the function APlog is supposed to clean up the stack frame in such a way that the caller gets exactly the state it was in before it called the function. So we save the return value in REX, right? So REX is the value used, at least by Linux, but also in practice by all other systems, to store the return value, and the caller knows this. The caller will assume that it can find the return value in REX. Next, we restore the old stack pointer from the base pointer. So remember, originally we stored the RSP into RBP, now we do the opposite. And this means that no matter what we did in between, such as allocating the local variables, we get back to the same stack location. That is, it effectively deletes the current stack frame. It's no longer included in the stack, because the addresses are now lower than the top of the stack, which is the lowest stack address that's really in use. Next, it restores the preserved registers from the stack. So if there were any that needed to be preserved, this is done now. It restores the old base pointer from the stack as well, because the caller will expect RBP to be unchanged. And finally, it returns to the caller. So by the time we get to red, everything except for the return address has been cleaned up, which means that the red can be done. So there is an alternative. There is a leave opcode, which performs these first two operations. So mov RBP, RSP, and pop RBP. So there's actually no point in having the leave opcode, in the sense that it does functionality that's already there in terms of other instructions, and this is actually somewhat common in Intel. It was originally done as an optimization, but no longer really serves any purpose. It's simply there for legacy reasons. But it still makes it look like the code is higher level and makes it easier to read. So there's at least that benefit. So finally, let's put everything together. Here we have a very simple function. This function, hello, actually contains a buffer overflow. But we're not thinking about that right now. We're just going to look, if we write this simple function in C, what happens in the assembly code generated by the compiler. So on the left-hand side, on the top, we see the C code. On the right-hand side, we see the result of the compilation with some comments indicating what this actually is. So let's take a look line by line. First, section RO data says that now we have a bunch of read-only data following. And this is there for the string. So this tells the operating system when loading the binary to load this in a place that is not writable and not executable, but it is readable. So we put the string there, and the string is simply the argument to printf, which we're going to use in the later code. Well, then we have .text, which essentially says this is where the code actually starts. And this, when specified in an L file, indicates that for the operating system that it must make this part executable. And on a modern system, also that it should not be writable. So we have hello, which is a label for the function. So this allows you to later jump to the label hello if you want. First, we save the old frame pointer as I discussed, push RBP, create the new frame pointer by moving RSP to RBP, and then we subtract 32 from the stack pointer. So we're reserving 32 bytes for local variables. Now why, you ask, would we do such a thing? We only have 16 bytes worth of buffer. However, it turns out that we're also going to store the name pointer. Right? As I mentioned, it's convenient to preserve parameters in local variables, because otherwise you cannot use the register they are stored in. So we need space for the name pointer, which is another 8 bytes. So that's 24 bytes. Why are we allocating 32 bytes? Well, it turns out that the compiler wants to align the stack on 16 multiples of 16 bytes for efficiency reasons. Right, so it's going to just allocate some extra space that remains empty as padding. Okay, next step. So now we're here. We move RDI, which is the first parameter. So by convention, the first parameter is stored into RDI to RBP minus 24. So this is a local variable stored in the stack frame. Well, next, we're going to pass this name as a parameter to the string copy function. Right, so here we load the value again from the stack frame and store it in RSI, which is used for the second parameter of a function call. Then next, we use the LEA instruction. If you remember, this was the load effective address instruction, and it loads the address stored in the memory reference. So the minus 16 RBP is not dereferenced, but rather computed and stored into RDI as a pointer. Now this pointer is passed as the first argument to string copy, so this is actually the destination pointer. So what do we have now? We're going to call string copy and ask it to copy from name to buff, an arbitrary amount of data, because the string may have arbitrary length. Okay? Next we have the call to printf, which is similar. First we load the second parameter into RDI using the LEA instruction again for the buffer, and then we have this reference RP relative to the string, which we also load as a pointer to the parameter, and then we pass it to the printf call. Finally, the leave instruction restores the old stack frame, as I mentioned, because it stands for two other instructions. And finally, we are back at the return address, and we call the ret instruction to jump back to the function that called us. Now, this concludes the lecture on assembly. I hope this gives you enough background to understand the low-level, gory details about attacks.